Okay, here we go. So what this is called an implicit function. And so implicit means it has the word, it's from the word implied, right? So there's no overt in-your-face function here, y is a function of x, but it's implied. It's kind of in the background. So, and that's what we called, say, an expression of x. Okay. So this is implied by this equation. It implies there is some expression of x that equals y. And so we call this an implicit function. An implicit function. And then finding the rate of change is implicit differentiation. Okay? Because we're finding the rate of change of y with respect to x for this implied function that we never really ever know. Okay? It's kind of hidden in the background. An explicit function are all the ones you did on your mastery test yesterday.
When do we get the scores for that?
I have to grade them. So when I grade them, but I'll send an email. All right, so this is an explicit function. It's y is a function of x, in your face, right? It's explicit, it's right there, it's overt. Okay, but whatever this y is as a function of x is implied, okay? So that we call this implicit differentiation. And so we start by taking the rate of change of both sides. So we're going to take the rate of change of e to the something, which is? The rate of change of e to the something is e to that something, but then, by the chain rule, times the derivative of the interior function. How are we going to do the derivative of that? Product rule. Okay, so we can do derivative of the first times the second plus the first times. Derivative of the second would be 1. But then you got another chain rule in there, right? Because implied is that y is some function of x. And so we need that. By the chain rule, we need the rate of change of y with respect to x. So that's the rate of change of the left side. Does that make sense? This side's easier. Rate of change of 8x. 8. Rate of change of 4y. 4, but times rate of change of y, rate of change of 3. 0. Okay? So that's our implicit differentiation right there. But now what we need is we need to get what we need in the end. We want what does the rate of change of y with respect to x equal. So what was our strategy for that? Get every term that has a y prime to the left and every term that doesn't have a y prime to the right. So we actually have 2 terms here. So we're going to have to distribute first. Distribute first. So go ahead.
Could we divide by index e to that on both sides and just?
Yeah, that'll work. Yep, that'll work. But then this is we're introducing a fraction or negative exponent, which maybe is not as ideal. But yeah, it'll work. It'll work. So I'm going to distribute. So here's just a tip that helps you keep track of things. Leave lots of space in between your terms so you know what your terms are, because sometimes we have so much multiplication that it all starts blending into one big blob, okay? But this is really about keeping your terms separate. So this is the first term. And then the second term is this thing multiplied through. Equals 8 plus 4y prime. So really keeping, even there's lots of things multiplied sometimes in each term. So keep those units together and get what you're adding, your terms added and subtracted, spread out. So that's where students end up making lots of mistakes, because the multiplication and addition it becomes this big kind of blob, and that's where mistakes happen. Questions about so far? Are we good? So next step would be get this over to the left, get this over to the right. So everything that has a y prime will move to the left. And can I also factor in one step? Is that okay? I'm going to do that. So this is going to move here, just over to the right side. And this is going to move, sorry, to the left, and this is going to move to the right. And then I'm going to factor out y prime. So the first term will be e to the x squared y times x squared. And then this one will be minus 4, right? Because when I move this over, it's going to be minus. It's going to be minus 4. And then this is going to move over, so it's going to be, we're going to have the 8, and we're going to have minus e to the x squared y. Stop me if I lose you. Everybody good? Does it make sense? Last step. We got it. So now all we need to do is divide by that term right there. So we've got 8 minus all over questions on that? Yep.
It's just more in general, but basically, for any time you have implicit differentiation, you're going to be using the chain rule. So that kind of threw me for a
Yes.
loop with the.
Yeah, and if I didn't emphasize that enough on Wednesday, I apologize. So I tried to emphasize that because this is what's implicit, what's implied, right? What's implied is y is some function of x. So every time you differentiate y with respect to x, you're going to have by the chain rule, you're going to have the rate of change of that, whatever that implied function is.
Okay.
And so that's where our y primes come from, that we end up solving for. Yeah. Every time you do something with respect to y, it's going to have chain rule. Other questions on this one? Okay, and let's look at number 4. So these are the ones you gave us the most trouble. Last chance on this one. Okay, cool. And then so number 4 is this one. So how do you know the point is on the curve? We talked a lot about this. So this thing here, I'll write it out bigger. How do we know that 2, 1 is on the curve? How do we know that it's a point on the curve? Yeah, if you plug 2 to 1 into this expression, it'll equal 27. How do we know this point is not on the curve?
Those coordinates won't equal.
Not well said.
Yeah, I know, I agree.
So can you say better?
If you plug the x and y coordinates of that point into the equation, it won't equal to
Much better. Okay, much better. Yeah. Okay. All right. So we want to write the equation for the tangent line in slope-intercept form, and what we like is our point-slope form. Remember that we always use this to build our piecewise functions, and so this is a lot more meaningful for us. So we can just start with this and then just rearrange it into point-slope form, the mx plus b. Okay. So what do we need here? We need a point on the line, and we need the rate of change, right? We need the rate of change, the constant rate of change of our line, and we need the point on the line. So, do we have either of those? Yes, we have 2, 1, right? So we have our point, which is the actual point on the line and also on the curve, right? So that's it. So all we got to do is get the rate of change of our line, this pink line that they're drawing. And that will be the same as the rate of change. We know local linearity, if we're to zoom in enough, it would be the same as the rate of change at that point on the curve. And so how do we get that? We're going to do, you're all thinking it, we need to find the rate of change. So to find the rate of change of this implicit function, we need to do implicit differentiation. So we have 8x plus 4y plus, I'm going to go fast, 4xy prime plus 6y y prime equals 0. Okay, and so then we'll have y prime times 4x plus 6y equals negative 8x minus 4y. And so we got negative 8x okay, so I just cruised through that. Anybody? Did I make a mistake? How about that? Did you follow everything I did? 4x plus 6y, move these over both negative, divided by that. Okay, got it. So rate of change is this thing evaluated at 2, 1. Will give us our rate of change. So negative 16 minus 4, check my work here, negative 20, 8 and 6, 14. So negative 10 sevenths. Okay, so, and that's about, give me a decimal approximation of negative 10 sevenths, negative 1 point. Quick. Negative 1.4. About. Okay, and so does it match the picture? So looking at what's happening here, that bigger? No, can't make that bigger. Okay, so does a rate of change of negative 1.4 make sense looking at that picture?
Can't make it bigger, it's a little upper right.
Oh, this thing right here. Thank you. Okay, over there. So does negative 1.4, does that make sense with what we're looking at? For a small change in x, does y go down about 1.5 times as much as x increases? Yeah. Okay, looks good. So then we've got our negative 10 sevenths is our rate of change. A is 2, B is 1, gets us the point slope equation of that line, and then we can just do a step or two to get y. They're asking for y equals mx plus b. Different b, right? This isn't the y-intercept, right? So this b is the y-intercept. Questions on this problem? I went fast, so I'll give you a moment to digest and ask. Those are the two most commonly missed. Last chance. Does it make sense? Okay. Also, and let's hand in today's homework. Okay, so we'll pick it up just to make a stack over here on the ends of the things. Okay, so I've got this scenario. So let's kind of bring some real-world application to this. What we're talking about. So there's this ladder here. It's red, and it's up against the wall, just flat against the wall right now. It's a 10-foot ladder. Okay, a 10-foot ladder, and we have this tricky monkey here. Because he's tricky and he likes to kick out the end of that ladder so that it slides and falls down. Okay?
Why?
What?
Why?
Why?
Means he just a jerk.
Yeah, he's just mischievous, right? Like all pet monkeys that are really short. Okay, so this is. So how can we define in this situation what the quantities x and y are? So can we say what is x and what is y? Can we define these quantities x and y well related to this falling ladder? So, and when I say x and y, I'm meaning this is still our x-axis and this is our y-axis. So what quantities relate? What exactly is x in this situation? Christian?
Would y be how high the ladder is up the wall?
Okay, so he's saying where. So he's saying where the top of the ladder is touching the wall. Is that a changing or a constant quantity? Changing, right? It's doing what? It's decreasing, right? So y is the height of the top of the ladder. Okay, in feet. All right, and so how can we describe what x is then?
The height of the bottom of the ladder,
Is that height?
length,
Okay, distance of
bottom of the ladder.
bottom of the ladder from the wall. And that's also in feet. Okay, so is it a valid kind of endeavor to talk about the rate of change of y with respect to x, to try to find and talk about the rate of change of y with respect to x here? Is that a valid endeavor? What'd you say? And what would it mean? What would the rate of change of y with respect to x mean in this context?
If you have too much free time, you should probably be doing.
Okay, that's one response. What would the rate of change of y with respect to x mean?
It's like based on, well, if you knew the rate of change of y with respect to x, if you knew how far away the bottom of the ladder was from the wall,
Okay.
then find out the height of the top of the ladder.
So what I heard you talk about is just the quantities. You said if you knew what x was, you could find what y was.
Yeah, if you knew the rate, or if you had the rate of change.
Do we need the rate of change to do that?
Because isn't y changing?
But you said if you knew x, right?
Right.
So if we knew x right here, could we find what y is?
Yeah.
And do we need the rate of change for that?
No.
Okay. So, but that's a valid. I mean, it's a valid thing that given one of those two quantities, we can find the other. But what would the rate of change of y with respect to x mean here in this situation, Steve?
How fast the top of the ladder is falling as the bottom of the ladder goes from the wall?
Yeah. So it would be like a speed, but would it be a speed with respect to time? Or would it be a speed with respect to?
The bottom of the ladder moving to the right.
Right. So for a change in the bottom of the ladder, we're saying what's the relative change in the top, right? We're saying what's given a change in the bottom relative to that change. How much does the top of the ladder decrease? That would be our rate of change. So how can we get that? Where does that come from? How can we? So we want to find the rate of change of y with respect to x. Where's that? How are we going to get that? Where's that going to come from? What do you need to find the rate of change in y with respect to x?
Either an x point and a y point, or one defined,
So like this, like
was that like 7 something?
7 point something. So he's saying if we have x equals, I'm just going to guess, 7.2 and y equals 5.9.
So you use like the point slope formula.
All right, so if we have that, then we can find the rate of change of y with respect to x. What do you think?
No, we need 2x points and 2y points, or 2x points and the rate of change in y, or 2y points. And
How have we been finding the rate of change the last 2 weeks? What do we need to have the rate of change?
Delta y over delta x.
Okay, and where's that going to come from? How are we going to get that? What's that? Someone said something? Second point, no. We want to get exactly. We don't want to estimate. We want to get exactly. Where is dy dx going to come from?
Well, I mean, you need a function to describe it, and then you put that in the open form.
Yeah, we need a relationship of y and x. We need the equation of y and x, and then we differentiate, whether that's explicit, like you did 10 yesterday on your mastery, or implicit. So we need a relationship. It comes from the relationship of y and x, whether explicit or implicit. This is not a subtle point, okay? This is not a subtle point. It just became, we took it for granted that to get an exact rate of change relationship, we needed the relationship of y and x first. Okay, so in relation to whether that's implicit or explicit, like all of your mastery ones, or implicit like we've just been doing the last day or two. Okay, so what is the relationship of x and y? What is the relationship of x and y? But when I say relationship, I mean the kind of relationship from which we can get a rate of change. So that's a true statement about the covariation. But when I say relationship, I'm saying I want something that's going to allow me to get this. What kind of, so what?
Choose point slope.
Point slope. So y equals m times x minus a plus b. Does it work? Ross? Was that a hand? Oh, okay, sorry. I thought you raised your hand. Molly? Constant of proportionality between them. Okay, so y over x is constant. So here's...
No, sorry, the change in them. That's what I meant to say.
Okay, that's true. When I show you now, you're talking about what the rate of change is. But we're still trying to get what's the relationship between these. Austin, any ideas? What do you think?
As one increases the set value, the other one's going to decrease that set value.
Right, but that statement is true, but it doesn't help us get this. See, when I say a relationship, I'm talking about a mathematical relationship. That's a true statement about the covariation, and it's important.
I know the value, but I'm just trying to get at that. Why and x equals something. So
Right, a mathematical, right, like a formula. So let's take a look at this. Someone else got an idea? What is that quantity right there? Is that the change in x? That's just x. That's the distance, right? And this is? And what's the length of the ladder? Does that help? Yeah, what is it, Kevin?
X squared plus y squared equals 10 squared. So 100.
Isn't that the relationship between x and y in this situation? What if we change x and y? Does that relationship hold? So it has to hold as x and y change, right? We need it to be true no matter what x and y are. So does that hold?
Yeah, because the ladder is always 10 feet, so your hypotenuse is always 10.
Yeah.
So here's a different triangle. So does x squared plus y squared plus 100 still hold?
Yeah, 'cause that angle's always gonna be right.
Right, so we'll always have a right angle, so we can always do the Pythagorean theorem. And so this will always be true as x and y change together. Okay? And so how are we going to get rate of change of y with respect to x?
Derivative of x.
And we are experts, right? 2x. Rate of change of y squared.
2y times y prime.
2y, y prime? 0. Okay? And solving for rate of change of y with respect to x, so I'm going to write it this way. Y prime. It's going to be
Negative 2x over 2y.
which equals? Here's a very appropriate place to simplify. Easy and okay, so let's look at where I've got it right now. Let's analyze. Go ahead.
I understand the x squared, y squared. Where'd the 100 come from?
So what is that right there? So where did this? Do you recognize that?
Oh, I see what you're. Okay, I see.
So what is this about?
That is the x plus the. Okay, I understand. I don't know how to say it, but it's the. You're saying 10 squared plus the y squared, which is 10 also. I understand.
So is this true for any x and y in all situations? X squared plus y squared? Why? Why in this situation?
Because your value is a 10-foot ladder, right? So
Okay.
it's 10 foot high or it's 10 foot long on the ground.
Okay. So I think you might not be seeing it. This is a right triangle. This is our relationship for right triangles. A squared plus B squared equals C squared. That's the only reason we can use it.
Okay,
If we don't have a right triangle, we can't use it.
I understand.
Okay? So this is about the Pythagorean theorem. It's a right triangle. Okay, so let's analyze what I've got. And I'm going to go a little bit further. I don't know if this is possible. Let's see. Perfect. Okay, so right now I'm going to say that x is 3. What's my y value?
9.5.
How about exactly? What's my y value exactly? Find it. Can you find it? That's what we started before we even talked about rate of change. We said if you knew the x, you could find the y. So find.
Yeah, it's 9. Yeah, you 3 squared plus 1.
Anybody get it? Is it the square root of 91?
Yeah.
And anyone get what the rate of change is then at this moment?
-3.
Negative? 0 point? Find it. So did you guys find it? Find the rate of change now at this moment. Find the rate of change of y with respect to x at this moment. As soon as you get it, shout it out. 314. Someone else get that? As an approximation? Okay, what does that number mean? So what does that number mean in the context? Tell the person next to you. What does negative 0.314, what is that referring to or representing? Go. Yes, it is the rate of change of y with respect to x. What does that mean in this context? So that's not a valid response. Yes, it's the rate of change of y with respect to x.
Oh, yeah.
Okay, and I'm going to give you another one. Y equals 6. Find x, find the rate of change. So here's the situation now. Y equals 6. Find x and find the rate of change. And then talk about that one. What does that one mean? Did you get 8?
Yeah.
And then therefore this is negative 1 point. Is that right? Okay. So interpret each of those, and then reason about them together, okay, in the situation. So interpret each value, and then reason about those values, comparing each, looking at the situation. Go, another conversation.
We know.
Yeah.
I know.
Well, yeah, we have our two rates. One is negative 0.
Okay, so what does negative 0.314 mean in this context? Alexander, want to give it a shot?
Whenever a little change in y,
Yes.
Okay, you said for a little change in y, the change in x is negative 0.314. Agree with that? Do you agree with that, Shana? He said for every little change in y, the change in x is negative 0.314.
Isn't it only when it's 3? Like
Okay.
3 feet away from the wall?
So when the bottom of the ladder is 3 feet away from the wall, for a little change in y, the change in x is negative 0.314. Ariana, what do you think about that? Agree with that?
That makes sense to me.
Makes sense to you, okay? Peter?
as x increases, I guess as the bottom of the ladder gets farther away from the wall,
Okay.
the top of the ladder gets closer to the ground at a faster rate.
That's what negative 0.314 means?
They meant
Nope, just negative 0.314.
Yeah, that's fine.
So as y changes a little bit, x will change negative 0.314. Negative 3.41 feet. Jonathan?
No, negative 0.314. That's the rate that y, the height is decreasing when x changes at a rate of 1.
When x changes at a rate of 1. Okay? Oh, I'm glad I asked this question. Brent?
Is it at x equals 3, every small change in x is going to make y change at a rate of negative 0.314?
And what does that mean, a rate of negative 0.314? So for a small change in x, y is going to change. How is y going to change?
Negative 0.314 times the change in x.
Right. It's going to fall about 31% as far as whatever your little change in x was. Okay? So this is the change in y with respect to x. So this is, we had it backwards. This is for a change in x, a small change in x. This is the fraction of that change that y will change, right? It will change it will decrease, y will decrease 0.31 times as much as x increased. All right, and then later on, now the height of the ladder is, so later on when x is 8 and y is 6, so who can interpret that number? Linman, can you try that one? What does negative 1.33 mean?
When x changed a little bit,
Right, when x changed a little bit.
y change is negative 1.33 times x change.
The y changes, so y changes more or less than x? Right, a third more, right? It's about like 1/3 more than x changed. See that? So well said. She said, as x changes a little bit, y is going to change negative 1.33 as much as x, or it's going to go down about 1/3 more than x changed. Okay? So then what's happening to the ladder as x increases? Yeah, so you got to watch out for falling faster because that implies what quantity that we're not talking about?
Speed.
Time. We're not talking about time here. I can make x change really fast in the beginning and then make x change really slow over here. Will it fall faster at the end then? No, it'll fall faster at the beginning. Do you see? So what is this really talking about?
Following the greater amount
Okay, per
small changes in x.
per small change in x. So this is all about the change in how y changes with a change in x. So to say that it's speeding up as it goes down, it's not specific enough, and it kind of sounds like you're talking about time.
So if we throw feet in there, I think it sounds.
So go for it.
Sounds better. So for a small change in feet of x,
Right?
y changes at, it decreases at 1 1/3 feet faster than the small change.
Okay. And so, and then that amount of change of y is getting more negative, right? It's getting more negative. So we have bigger drops for the same change in x. We're going to get bigger drops in y as x increases. Okay, is this an increasing rate of change or decreasing rate of change? Is this increasing rate of change or decreasing? Okay, so I heard decreasing. Anyone want to say increasing? Increasing? Okay, this rate of change is getting more negative. Would you agree? So values that get more negative, increase or decrease? It's a decreasing rate of change. So we're going to talk more about that in a couple weeks, or coming up soon. But just wanted to give you a preview here. This rate of change is becoming more negative, so that's a decreasing rate, even though the magnitude of the rate is increasing.
I'm reflecting back on this. It's decreasing, but at a
We did this in.
increasing rate. Or it's
Don't try to combine them. Just talk separately. What is y doing? Y is decreasing.
Got it.
What is the rate of change doing? Is it decreasing or increasing? The rate of change is decreasing. Okay, so questions on that. So here's using implicit differentiation to talk about an actual problem. So let's do it. Let's look at a variation of this now. Any questions? This is what I want. Okay, so this is what we had, right? We had the relationship between the quantities, which enabled us to get a formula for the rate of change of x with respect to y. Now let's bring time into it. So we said time's not involved here, but now let's bring time into it. So let's suppose that x is changing at a constant rate of v. Okay, so v is the constant rate of the bottom of the ladder moving to the right. So it's the constant speed of the bottom of the ladder. So we could, so the rate of change then is obviously just v. It's the constant rate of change, right? And that follows our rule that it's a constant multiple times function, but that's the constant speed. And so what would it look like now to take this here, and instead of differentiating with respect to x, we could differentiate with respect to t, and look at this whole thing and bring time into the situation. Okay, so with respect to t then, what would the derivative of x squared be? So now notice that x is a function of t, right? So what would the derivative of x squared be with respect to t? Yeah.
2x times x prime.
Right. 2x now we have chain rule because x is a function of t, and that's what we're differentiating with respect to. So 2x would be 2x times the derivative of x with respect to t. And then what about y squared? So what would that be? So we're differentiating y squared with respect to t. Jamal? 2y. Is that it? times y prime times y with times the derivative of y with respect to t. Okay, so in 100 with respect to t, the rate of change of 100 with respect to t is still 0, right? As time changes, 100 stays constant. So we get this situation, and we can what we have here now is an equation that has two rates in it, not just the rate of change of y with respect to x, but this equation brings together a relationship of two rates. How x is falling, how x is changing with respect to time, and how y is changing with respect to time. Does it make sense? So because of that, this is called a related rates equation. It's an equation that relates more than one rate. This is the first time we've ever seen that. In any given situation, we've always only looked at one rate of change. So now we're saying, look, x has a speed, y has a speed. This equation then relates those speeds together. So we call it a related rates equation. So where did the related rates equation come from? Where did it come from? So if we want to get a related rates equation in a situation, where's it going to come from? Where are we going to get that from? What's the source? Sterling. Where's that related rates equation come from?
From the x prime, right?
That's still the rate. So these are virtually the same. They're both just different forms of the related rate equation. Where does it come from?
The third variable that you're adding,
What's that?
the third variable you're adding.
Okay. But so how did we get that equation? How did we get it? It's the same question I asked earlier. Yeah.
How x and y change with respect to t, or the relationship.
Yeah, it comes from the equation that relates the associated quantities, right? So we still have x and y, but now we're thinking of them as functions of t. So we need this first, right? We need this. In order to get a related rates equation, we need the equation that relates the quantities. And so in solving these applications, this is a huge idea, and if you don't kind of connect with this, you just will stumble in these problems. We want a related rates equation. That's our goal. How are we going to get there? Well, first we need the equation that relates the quantities. And then from there, it's just differentiation. Okay, so let's try an example. So here's a related rates example. So the edges of a cube increase at a rate of 2 centimeters per second. How fast is the volume changing when the length of each edge is 50 centimeters? Okay, so here's kind of a strategy. Here's a strategy for thinking about this, and it goes right. It's all about what I just said. It's all about what we just said on the previous slide. We want to relate rates here. What are the two rates that we want to relate in this situation? What two rates of change are we trying to find a relationship for?
Change of volume and
Christian, go ahead.
The rate of the edges of the cube.
Okay.
And the rate of the volume.
Right, so the rate of change of the edges of the cube with respect to time, and the rate of change of volume. So where is that going to come from? Where's that rate of change function going to come from?
The volume.
Okay, so can you say more? So if we want to relate the rate of change of volume with the rate of change of edge length, what do we need to do that? I'm talking more generally, yeah. Okay, but I'm talking more generally. So what kind of thing do we need?
Oh, something to relate those two, to associate those two equations.
Which two things?
Length of the edge of the cube.
The edge length and we need a relationship of edge length and volume in order to get a relationship of the rate of change of edge length and the rate of change of volume. Okay, so here's kind of a strategy. Identify the rates involved. We already did that. Okay, how fast the edge length is changing, how fast the volume is changing. So identify the quantities associated with those rates and assign variables. Okay. So what is if we're talking about how fast the edge length is changing, what's the quantity associated with that rate of change? Edge length. And if we're talking about the rate of change of volume, what's the quantity associated with that? Volume. This is like the easiest step. So then we need, so let's call edge length S, we'll call volume V, and time T. And so what do we need? We need a function or equation that brings those quantities together, because then from that, that's the source of how we're going to get the relationship of the rates. So now we've got edge length of a cube and volume. What function or equation is going to bring those two together? Yeah, Gilbert.
Volume equals side cubed.
Volume equals side cubed, right? So volume as a function of side length, volume equals s cubed. How are we going to get the related rates equation? Rate of change of volume and rate of change of side length. Where's that going to come from? Or what are we going to do? Are you all thinking it? Jonathan? So now we want to bring rate of change of volume and rate of change of side length into this. How are we going to do that? You did it yesterday.
You take
35
the-
times.
Is it, you change the,
Go ahead. Sorry, he just, yeah.
So we're gonna take the
Derivative, right? Derivative, right? Derivative gets us rate of change. And in this case, we're going to use implicit differentiation. So what does that look like? So we're going to do derivative of volume with respect to time. And derivative of side length with respect to time. Okay? So derivative of side length with respect to time, 3s squared, and then by the chain rule. So now we've got chain rule on everything we do because everything is a function of time. So another way to think of that left side would be, what's the derivative of v? What's the derivative of v? It's 1, right? So it's like 1 times v, right? 1 times dv dt by the chain rule. So derivative of 1 times your variable is just 1, and then time by the chain rule dv dt. Okay, so we get dv dt equals 3s squared. And what was dsdt? That was given, right? The rate of change of the side length was 2. So that's right there is 2. That's our rate of change of side length with respect to time. So here is our, this was our related rates equation. But we know that the side length is always changing at a constant rate of 2. So we can put that 2 in there. And then we want to know how fast the volume is changing when the length is 50. So what are we trying to solve for there? We're trying to solve for dv dt or s. How fast is the volume changing? dv dt. When the side length is 50, and that's what we called s. So we're evaluating this rate of change of v when s is 50. That's this notation that we've seen a couple times. So my experience is that this overall strategy doesn't come easily. So I'm saying it over and over and over again. So somehow we got to file this away and get it into the forefront of your thinking when you're solving these problems. Our goal is a related rates equation. Where is that going to come from? We need a related rates equation. Steve.
Well, the relationship between the two quantities.
Yeah, exactly. So first we need to build the relationship between the quantities. And then we use differentiation to get that. So we have a long weekend. Can I, for those who need to leave, can I ask you to watch the video? Can we do 5 more minutes? And those who can stay, can stay? Is that okay? Because we got a long weekend, and so I want to make sure you're prepared for the homework. And then I'll give you 5 minutes back on another day. Okay? Is that fair? We don't have class on Monday. Okay, so can we do that? Is that okay? So then, to make that as quick as possible, if you're leaving, please be. All right, you guys, can you quiet down? Just don't talk, please. Just slip out quietly if you need to. Watch the video. Okay, here we go. So here's another example. See if you can do this. Rates involved.
Oh, I was just saying, what is that initial time?
Okay? That's right. Rate of change of radius, rate of change of volume with respect to time. Okay, next thing to do is, what are the quantities associated with these rates? So what's the quantity associated with the rate of change of radius? So this is the easiest step. What's the quantity associated with the rate of change of radius? Radius, right? The quantity that's changing is the radius. And then this one is volume. So I've already assigned variables, R and V. So if we want the related rates equation, what do we need to get the related rates equation?
An equation that associates the two.
To what? Which?
Radius and volume.
Right, so to get the equation that associates these rates, we first need the equation that associates R and V. And what is that?
Volume of a sphere.
Volume of a sphere is
4/3 pi r cubed.
4/3 pi r cubed. That's the same step. So this is our 4/3 pi r cubed. And from that, we can get the related rates equation. So we differentiate everything with respect to t. Rate of change of v with respect to t is 1 times dv dt. Rate of change of r with respect to t. Okay, so we're going to have 4/3 pi. We're going to hold on to that because it's multiplied, right? And then times 3r squared times. This was the goal of the whole thing. This is the centerpiece of this problem, the equation that relates the rates. Where did it come from? The equation that related the associated quantities. Okay, and then, so what are we solving for? What does it ask for?
How the radius, or how fast, rate, radius.
This is our unknown this time, right? So in order to get that, that means we need to know everything else. Everything else must be known if this is what we're going to solve for. Do you see? So somehow we need to know what is dv dt. Do we know that?
Yeah.
That's our 150, right? And then we need to know the radius at this moment. What's the radius?
4.9237.
How'd you get that?
I calculated it from the volume, the first.
Yeah, so we're given, good, excellent. So we're given the volume. So in order to get the corresponding radius, we have to come here and get our radius for a volume of 500. Tell me what you got?
I'll need a simple feature. 4.923.
That sounds great. And that's inches. So we got 3 times 4.923 squared times our unknown dr dt. Okay, any questions? So you can finish from there. All you're solving for the rate of change. Did anyone get it? A value? So you should think about what that value means. The units are inches per minute. and be able to interpret that number, right? That's a rate of change, so should be good at interpreting that number in inches per minute.